Hello all of you and welcome to your chemistry session. In this video we are going to discuss the periodic table, and specifically we are going to look into the trends of properties in periodic table. To begin with, let's understand why was there a need for making a periodic table. If you look at this picture, there are three conical flasks on the screen, and each of the conical flasks consists of a chemical substance. In the first flask, it consists of chlorine, the second consists of bromine, and third consists of iodine. Each of these elements, they look very different from each other. Chlorine is a gas, bromine is a liquid, and iodine is a solid. They all of them have very different physical properties. But when each of these elements combined or reacted with sodium, each of these substances, they formed the respective salts. So chlorine formed sodium chloride, bromine formed sodium bromide, and iodine formed sodium iodide. Now each of these salts which were formed, they all look very similar. All of them are white solids, and they all of them can dissolve in water to form solutions and also conduct electricity. So it was these differences in properties which separated chlorine from bromine and iodine. However, all of these compounds showed some common chemical properties, right? Which shows that each of these compounds underwent a similar chemical reaction. So understanding a trend basically among the elements enables you to predict the chemical behavior of the elements. The trends and properties of the elements in group or period can be explained in terms of their electronic configuration. To understand how the elements are arranged according to their electronic configuration, let's first understand the structure of a periodic table. So in a periodic table, you have vertical columns which are known as groups. A particular group contains the same number of valence electrons, or a particular group contains similar electronic configuration. The horizontal rows in a periodic table are known as periods, and the elements present in a particular period, all of them contain the same number of energy shells. Okay, to recall, energy shells are these imaginary paths along which an electron orbits around the nucleus at a certain velocity. So this is what a periodic table looks like. You have studied how different scientists like Mendeleev, Newland, and finally Moseley arrived at this periodic table. The table has been divided according to the properties of the element. The periodic law over here it states that the properties, the physical and the chemical properties of the elements are a periodic function of their atomic number. What that means is that the elements in this periodic table have been arranged according to their atomic number. The atomic number of an element is equal to the number of protons present in the atom of the element. So in this periodic table, you can see there's a legend over here, and each group has been given a different color to show the different kinds of elements having different properties. For example, this pink extreme left corner group is called the alkali metals. Broadly, a periodic table is classified as main group elements, transition elements, and rare earth elements. So the main group elements are present on either side of the periodic table. The groups 1, 2, and 13 to 18 are your main group elements. Then you have the transition elements. Transition elements are present from group number 3 to 12. They are present right in the center. Some of the most important metals belong to this group. For example, copper, zinc, iron, all of these belong to the transition metals. Rare earth metals are these two rows of elements which have been written outside the body of the periodic table. Now, these two rows actually don't belong there. The first row is called the lanthanide series, and they follow the element lanthanum in the sixth period. And the second row is called the actinide series, which follows the element actinum in the seventh period. The groups have been given Some of the groups have been given specific names. For example, alkali metals are elements which consist of the most reactive metals. Lithium, sodium, potassium are some of the examples of elements from group 1A. Alkaline earth metals are the second group elements, and these are also reactive, but they are relatively less reactive than the alkali metals. In the diagram, you can see a picture of magnesium which has been placed on a watch glass. Halogens are elements which are present in group 17. They usually consist of non-metals which are reactive. In the diagram, you can see a picture of bromine that is being placed in a conical flask. Noble gases are elements which are in the 18th group in a periodic table. They are inert gases because they are highly stable and they do not react readily with substances around them. If you notice, most of the elements in the periodic table are made up of metals. Hydrogen is actually a non-metal that has been written on in the same group as that of alkali metals. It is because hydrogen has only one electron and therefore has only one valence electron. So, because of that reason, it has been placed in the alkali metal group. However, hydrogen is a non-metal. Let's look at these three elements, lithium, sodium, and potassium. These three elements belong to the same group 1. Okay. However, each of them react very differently with water. So to understand the reason why does lithium react differently or less vigorously with water as compared to sodium or potassium, or why does potassium react so violently with water, we need to understand the properties and their trends in a periodic table. So the first property that we are going to look at is the atomic radius. Now, the exact size of an atom is very hard to determine. An atom's size basically depends on the volume that is occupied by the electrons around the nucleus. And the electrons do not really move in well-defined path like we have mentioned over here. It looks more like this. So you have a dense center of protons, and then you have the electrons distributed around it. Okay. Now, what is atomic radius? Atomic radius is the distance from the center of the atom to the outermost energy shell. That is the atomic radius. Now, an atom of an element may or may not exist as a single atom. It may or may not be monoatomic. In that case, we need to look at the kind of compounds that the atom forms. For example, there are two kinds of compounds which are possible. One is an ionic compound and the other is a covalent compound. In an ionic compound, the atom forms an ion and then the electrostatic force of attraction of the oppositely charged ion holds the ions together, thereby forming a stable molecule. In a covalent molecule, however, the atoms share electrons between themselves to form a stable compound. So if I want to understand the ionic radius, I need to know the radius of the cation which is formed and the radius of the anion which is formed. Right? In a covalent radius, the atomic radius will depend on the distance between the two nuclei divided by 2. So that will give me the radius of a single atom in a covalent molecule. So let's try and understand atomic radius a little bit more in detail. Now let's try and understand what happens to atomic radii when we go across a period. So when we go across a period, we notice that in a particular period, for example, if we take this second period, the number of energy shells are remaining constant. lithium to fluorine, the number of energy shells are all the same. However, the number of protons increases. Because the number of protons increases by 1, the number of electrons also increases. Now, because the number of protons and electrons both increase when we go from left to right in a periodic table, the nuclear charge, what is nuclear charge? Nuclear charge is the charge of the nucleus. And nuclear charge depends on how many protons are there. Lithium has 3 protons, so it has a lesser nuclear charge as compared to fluorine, which has 9 protons. Okay, so as we go from left to right, the nuclear charge is also increasing. How does that affect the size of the atom? If the nuclear charge increases, then the valence electrons experience a much stronger pull towards the nucleus. Because the electrons and the protons are oppositely charged, the valence electrons are going to experience a much more stronger pull towards the nucleus. Now, the nuclear charge being more in fluorine will pull the electrons much more closer in fluorine as compared to lithium. Which is why, if the valence electrons are attracted towards the nucleus, the size of the atom tends to decrease. So the factors here are the number of energy shells and the nuclear charge. In this, across a period, we see that the number of shells remain the same, but there is increase in nuclear charge, which decreases the size of the atom as we go from left to right in a periodic table. What happens to the atomic size as we go down a group? When we go down a group, we see that the number of energy shells increases. So let's look at this group 1. We see that on going down, there is an increase in number of shell by 1. As the number of shells increases, what happens? The valence electron is moving further and further away from the nucleus, right? Which means that although there is going to be an increase in nuclear charge, because hydrogen has only 1 proton, lithium has 3 protons, and sodium has 11 protons, there will be increase in nuclear charge. But because of the increasing distance from the valence electron from the nucleus, it is not going to experience that much of an attractive pull towards the nucleus. Therefore, the atomic radius of the atom as we go down increases. In this diagram, we can very clearly see what happens to the atomic radius as we go across a period and as we go down in a group. Our next periodic property is ionization energy. Ionization energy is the energy required to remove an electron from an atom. If we consider this lithium atom, lithium consists of 2 energy shells. In the first energy shell, there are 2 electrons, and in the second energy shell, there is only 1 electron. In a neutral lithium atom, the number of protons and electrons are same. When I supply energy to this lithium atom, the energy that would be needed to remove this electron from the valence shell of lithium is called the ionization energy for lithium. To understand what happens to ionization energy across a period and down the group, the 2 important factors that we look at are the atomic radius and the nuclear charge. So across a period, when we go from left to right, we have learnt that the atomic radius decreases, and that happens due to the increase in nuclear charge. If the nuclear charge increases and the size of the atom decreases, the valence electrons or any electrons in the outermost shell are pulled more strongly towards the nucleus. That means that this particular element, fluorine, will have a greater difficulty to lose an electron from the outermost shell as compared to lithium. The lithium atom, being a comparatively larger atom, can easily remove the electron from the valence shell. Therefore, lithium has a lower ionization energy, and as we go across the period, the ionization energy of fluorine is much higher. So across a period, we see a trend of increase in ionization energy. What happens to ionization energy when we go down in a group? Again, we look at the same two factors, atomic radius and the nuclear charge. When we go down a group, we see that there is an increase in atomic radius. So that is due to the increase in the number of energy shell. Because when we go down a group, there is an increase in nuclear charge, but the valence electron is moved further away from the nucleus due to the increase in the number of energy shell. Okay, suggesting that the ionization energy decreases when you go down in a group. In this, you can see a three-dimensional representation of increase in ionization energy across a period and also decrease in ionization energy when we go down in a group.